Good evening, dear students. Yes. So today we are going to start with the next organic chapter, okay, from your chemistry syllabus, that is hydrocarbons. Okay. So what do you mean by hydrocarbons? Yes, what do you mean by hydrocarbons? In hydrocarbons, what you're going to study in the chapter hydrocarbons? Yes, anybody? Anybody knows what do you mean by hydrocarbon? What are hydrocarbons? Yes, carbon and hydrogen compounds, right? Organic compounds. So organic compound which consists of carbon, hydrogen, right? Oxygen. So hydrocarbons. So the organic compounds made up of hydrogen and carbon atoms, right? So here, so in this chapter, so what is covered in this particular chapter is mainly what are saturated compounds, what are unsaturated compounds, okay? Then in saturated, you have something called as alkanes, right? In unsaturated, you have alkenes and alkynes. What do you mean by alkanes? Alkanes means they are the saturated compound, that is the carbon-carbon having single bonds in between the carbon-carbon. When you have single bonds, then they are called as what? Saturated. Okay. And when you have carbon double bond or triple bond, okay, in between the carbon atoms, when you have a double bond or a triple bond, then it is called as what? It is called as unsaturated compounds. Okay. Now in unsaturated compounds, okay, so your alkanes, sorry, your alkenes and alkynes. So when you have a double bond, okay, when you have a double bond, then they are called as what? They are called as alkenes. And when you have a triple bond, it is called as what? It is called as alkynes. Right. So here in this chapter, it is mainly we are focusing here on the IUPAC system again. Okay. Then about the preparations, okay, preparation, physical properties, chemical properties, how they react, okay. So these all things are discussed in this particular chapter. So as we are going to solve the questions, okay, so like that I'll be discussing about the concepts, okay, fine. So let us start with the questions. Okay. So the angle strain in cyclobutane is. So what is the angle strain in cyclobutane? Okay. So this was a question asked in 2008. Okay. So angle strain means what? Cyclobutane. How do you represent cyclobutane? Cyclobutane is a cyclic compound. Okay. So this is a cyclobutane. Okay. Butane means four carbons. Right. Butane means four carbons. Cyclo means in the form of a ring, okay, in a cyclic ring. So this is a cyclobutane. So this is cyclobutane. So what is the angle strain? So what is the angle strain in this cyclobutane? Yes, anybody? So this is a theoretical type of question, okay? Yes, okay. Option B. Okay, Murli and Hema have answered as option B. Okay, now, so how we are going to observe that angle strain? Yes. So angle strain. Okay, angle strain is nothing but the strain which is obtained by the compound or the molecules. Okay, from their ideal angle. So whatever the ideal angle is there. Okay, from beyond that, when it's deviate, then it is called as a angle strain. Okay, now cyclobutane. Now cyclobutane is what? It is a ring structure, right? It is a four-member ring structure. You can see here, right? Now here it's you can see that the each corner, okay, each corner of the your this is 90 degree, right? Each corner of the ring is what? It is 90 degree, but there will be some angle strain, okay, occurred in this cyclobutane, so that it is 9 degree 44 minutes. Okay, so this is the your angle strain seen in cyclobutane. So it is 9 degree and 44 minutes. Okay, yes, Tejaswini has also answered it right. Fine. Let us go for the next one. The reagent used to convert an alkyne to alkene is. So, which is the reagent used to convert alkynes to alkene? So, to convert the triple bond into double bond, okay, which is the reagent we are using. Okay, so first one is zinc, Hg, HCl, B, palladium in the presence of H2, C, zinc in the presence of HCl, and D, tin in the presence of HCl. So which is a reagent which is used to convert and alkyne to alkene, so from a triple bond to double bond. So what we are doing, we are adding here. So when a triple bond is broken into double bond, there is an addition of hydrogen. Okay, there is hydrogen. Okay, now if you see this, now you can, if you see this, what you can see in this compound, what you can see that there is an addition of hydrogen, right? So for converting the alkynes into alkenes, what we are using? We are using a hydrogenating agent. So which is the hydrogenating agent here? So alkynes. So alkynes, okay. So if you do hydrogenation, hydrogenation means what? Addition of hydrogen. Okay, hydrogenation means hydrogenation. Hydrogenation means addition of hydrogen. So when we are doing addition of hydrogen, okay, we can use nickel, we can use, so this is the best hydrogenating agent like nickel, palladium, okay, then platinum. So these are the different catalysts which we can use. Okay, so here we can use nickel, palladium. So you can use your palladium. Okay, among this option, B option you can see palladium is used. So either of this you can use palladium, nickel, okay, or platinum. So these can be used in the presence of what? In the presence of H2. Okay, and what you're going to get? You're going to get a alkene. Okay, you're going to get a alkene. So this is a hydrogenation reaction. So when you're converting alkynes to alkene, so it is a hydrogenation reaction. So you can use either of this reagent. Okay, so option number B. Option number B is the correct answer. Yes, Hema has answered it. Very good. Okay, I hope it is clear. Hydrogenation means addition. Dehydrogenation means what? Dehydrogenation means it is removal. Okay, we are removing. Dehydrogenation means we are removing hydrogens. Okay, so this is a hydrogenation. Next question. In electrophilic aromatic substitution reaction, the nitro group is meta-directing because it A, decreases electron density at meta position, B, increases electron density at meta position, C, increases electron density at ortho and para position, and D, decreases electron density at ortho and para position. So when we are doing a electrophilic aromatic substitution reaction, so whatever the nitro group is there, it is a meta-directing. Now, with respect to the parent, okay, with respect to the parent compound, okay, so this is called as what? This is a ortho, okay. Then with respect to this is a para position, okay. This is this both are ortho, and with respect to your this is your meta position, right? So remember this. So if you have a nitro group, why it is meta directing group in the aromatic electrophilic aromatic substitution? What is the reason among this four? Yes, nitro group is a electrophile, right? Nitro group, nitronium ion is formed whenever we are doing nitration. So in nitration, we are using your nitrating agent like concentrated HNO3 and concentrated H2SO4. So from this, we produce this nitronium ion. This nitronium ion is a good electrophile. Okay, so what it does, it undergoes a electrophilic aromatic substitution reaction. Okay, and it is what? It is a electron withdrawing group, right? Electron withdrawing group. Nitro group is a electron withdrawing group. So what it does, so it has a minus I effect because electrons are withdraw. So whenever it withdraws the electron towards itself, so it will have what? It will show minus I effect. Okay. So because of this minus I effect, okay. If we write the structure, because it is a electron what withdrawing group. So if I write the resonance structure, so from this resonance structure, you can be able to see that the nitro group, what it will do. So first, let me write the resonance structure. Okay. So these are the resonating structure. Okay. So this is the resonating structure of your nitrobenzene. Okay. Yes. So here what you can see, this nitro group. Okay, when you see the nitro group, what it is doing, it is withdrawing the electron. Okay, from where, which position it is withdrawing? Let us see, it is withdrawing the electrons from the ortho and para positions, right? At the ortho positions and the para position. So the electrons are being withdrawn. So meta position, what it becomes? At meta position, it is having high electron density because electrons are not withdrawn from the meta position. Only at ortho and para position, you can see the electrons are withdrawn. But at meta position, the electrons are not withdrawn. So because it has not withdrawn, so the density, electron density at the meta position, it will be higher. So because of that, the electrophilic substitution, it takes place at what? It takes place at the meta position. So what is the reason? Now you can tell me. Okay. Hema has answered it as D. Very good. Okay. Yes, D is the correct answer. So, because it decreases the electron density at ortho and para position. Because when we write the resonance structures, we have seen that at ortho and para positions, you can see the electrons are withdrawn more. So, because the electrons are withdrawn more, the electron density will be less there. But at meta position, the electrons are not withdrawn, thus the electron density will be more. So at meta position, that is nitro group is meta directing group. Okay, because electron density is high. So the reason is decreases electron density at ortho and para position. Yes. Option number D. Yes, Tejaswini has also answered it. Very good. Okay. I hope it is clear. Fine. So remember that nitro group, nitronium ion. Okay, how this nitronium ion is, how we get this nitronium ion? Nitronium ion is we get it in nitration. Okay, how nitration is carried out? We are using a nitrating agent that is concentrated HNO3 and concentrated H2SO4. So by using this, we are going to get the nitronium ion. Okay, this nitronium ion is a it will undergo electrophilic aromatic substitution reaction. So because when we just now we saw that after writing the resonance structures at ortho and para position, the electron electrons are withdrawn, the electrons from the ortho and para position, they are withdrawn more. Okay, so the electron density will be less there. So at meta position, the as the electrons are not withdrawal, so there the electron density is high. So nitro group is a meta directing group. Okay, so option number D is the answer. I hope it is clear. Okay, let us go for the next one. The electrophile involved in the sulfonation of benzene is the electrophile involved in the sulfonation of benzene is A, SO3, 2 minus, C, B, hydronium ion, C, SO3, and D, SO3 plus. Which is the electrophile which is involved in the sulfonation of benzene? So for sulfonation, okay. So sulfonation is carried out in the presence of what? H2SO4. Okay, so when H2SO4 is, we have to take H2SO4. So this H2SO4, what it will form? HSO4 minus plus SO3. Okay, plus H3O plus. Okay, so here, which is the electrophile? It is the SO3. So SO3 is the electrophile. So remember that for sulfonation. Okay, so sulfonation of benzene, what it involves? So what we are going to do? We are going to take the the electrophile is produced, okay, by that is with the help of concentrated H2SO4. Okay, concentrated H2SO4. So it is SO3. Yes, Murli and Tejaswini and Hema have answered it correct. Very good. Option number C is the answer. So for sulfonation, which is the reagent, so benzene. Okay, so benzene again, when it undergoes sulfonation, SO3. So SO3 is the electrophile. Okay, which will undergo electrophilic aromatic substitution reaction. Okay. Next one. The carbon-carbon bond length in benzene is the carbon-carbon bond length in benzene is. So this is the benzene structure. Okay. So what is the carbon-carbon bond length? So what is the carbon-carbon bond length? How is the carbon-carbon bond length? Same as in C2H4. Same as in C2H4. This is C2H4. That is ethene. Same as in C2H6. C2H6 is what? Your alkane. Okay. Or C2H2. C2H2 is what? Your alkyne. Okay. Again, C2H4 is your alkene. Alkene and alkyne. Third option. And fourth option is alkane and alkene. So the carbon-carbon bond length in benzene, how it is? You can see that alternatively single bond and double bond is present. Okay, so this structure can also be written as, right? So why? So there is a delocalization of electron, right? So there is a delocalization of electron. So in benzene, due to delocalization of this pi electron, okay, all the CC bond length. So either you can write the bonds like this or like this. So the electrons are delocalized within the benzene ring. So all the carbon-carbon bond, okay, they are having double bond character. So they are having what? They are having the double bond character. Okay. So double bond character is present in between the carbon-carbon bond. Okay. So thus it is having this as alkane and because alternatively single bond and double bond are there. Okay. So alternatively one single bond, double bond, single bond, double bond, and these electrons are delocalized. So all the bonds are same. As we are seeing, all the bonds are same. That means they are having the double bond character. So the carbon-carbon bond length, it lies between the alkane and the alkene. So option number D. Option number D. Is it clear? Option number D is the answer. Why? Because alternatively double bond and single bond is present. But the electrons are delocalized. As the electrons are delocalized, the bonds are same. Okay, as the bonds are same, all they are having double bond character. So as they are having double bond character, so the bond length will lie between alkane and a alkene. Is it clear? Okay. Let us go for the next one. Which one of the following conformations of cyclohexane is the least stable? Which of the following conformation of cyclohexane is the least stable? So you might have studied something called as conformations. Okay, boat form, chain form, twisted boat form. Okay, so out of this all four conformation, okay, when we see the chair form, so this is the chair form like this. Okay, this is the chair form. Boat form is like this. Okay, then twisted boat is a little in twist form. Okay, same. And your half chair, how will be a half chair? Half chair will be like this. Okay, so here when we see chair and when we see half chair, okay, so half chair is the least stable. So the half chair, how it is obtained by when you are moving this C1 and C2 carbon. Okay, C1, C2, C3 conformation, it is moved and it is stretched, right? So you can see that it is, you can see in this, it is a least stable. So option number A. Yes, option number A is the answer. So when we see here, all the atoms are at the far distance, right? So they are in the stable form. In the chair form, they are in the stable form. Here also you can see both, right? All the carbon atoms are at a specific distance. Now here in the half chair, okay, what is happening? Your C1, okay, C1, C2 and C3, C4 carbon, okay, they are in one plane, and your C5 and C6, right? Here how it is in above and below the plane, all have come in one plane in the half chair. Okay, so half chair is the least stable. So remember that when if they ask you which is the least stable conformation of cyclohexane, it is half chain. Okay. Which one of the following has the most nucleophilic nitrogen? So which is having the most nucleophilic nitrogen? Nucleophilic means electron rich. Nucleophilic means electron rich. Okay. So they have asked which of the nitrogen atom is electron rich. Okay, which of the following, in the following compounds, everywhere there is a nitrogen. So in which of the following compound, okay, you can see where nitrogen is most nucleophilic. Yes, anybody? Anybody? The answer is option number B. Okay, answer is the most nucleophilic nitrogen is option number, sorry, uh, option number A. Okay, it is option number A. So option number A, here you can see that it is the most, you can see most nucleophilic. Okay, because see here, when we, So the electrons are there. So they will undergo what? They will undergo delocalization of electron. Okay, so the electrons are here. Okay, pi electrons are also there. There is a lone pair of electrons are also present. So it is highly nucleophilic. When you see option number B here, okay, here the lone pair of electrons, what it is, you can see there is a aromaticity present in this compound. Okay, so these lone pair of electron, they are the part of this aromaticity. Okay, so they, because of that, it is not so nucleophilic. Okay, that is not nucleophilic. These lone pair of electron, they are the part of the aromaticity. So, and in option number C, you can see nitrogen is present. Okay, it is present to the benzene ring. But here you can see COCH3. So this is a electron withdrawing group. So as it is electron withdrawing group, again the nucleophilicity of the nitrogen is reduced. So again, this is also not so nucleophilic nitrogen. Then here when you see option number D, okay, what you can see in option number D, this nitrogen atom. Okay, so again what it will do, it is a part of the benzene ring. Okay, it is a part of the resonance. So again, this is also not so nucleophilic in nature. So option number A is the answer. So option number A is the answer. So pyridine. So pyridine is the most nucleophilic uh, nitrogen. So it is having the most nucleophilic nitrogen. Which one of the following is the most energetic conformation of cyclohexane? Which is the most energetic conformation of cyclohexane? Most energetic conformation means it should be least stable. Okay, remember that when they ask you most energetic conformation means it is a least stable. So which is least stable? It is half chair. Okay, least stable and most energetic conformation of cyclohexane, okay, is half chair. Remember this, half chair is the least stable and more energetic conformation. Ethyl benzene cannot be prepared by. How does ethyl benzene cannot be prepared by? Ethyl benzene cannot be prepared by. Ethyl benzene cannot be prepared by. A. Woods reaction, B. Woods-Fittig reaction, C. Friedel-Crafts reaction, and D. Clemenson's reduction. Yes. Ethyl benzene. Can it be prepared by Woods reaction? In Woods reaction, what we want? We want both the alkyl alkanes, right? We want alkyl halides. So we want what? Alkyl halides in the your Woods reaction, right? Both should be alkene, but here we have in the compound only there is a aryl group. So Woods reaction. So which cannot be prepared by Woods reaction is the ethyl benzene cannot be prepared by Woods reaction is by your Woods reaction. Okay, ethyl benzene cannot be prepared by which reaction? It is Woods reaction. In Woods-Fittig reaction, one of the R group can be your, in Woods-Fittig reaction, one of the alkyl group should be a substituted aryl halide, and another will be your I can take this CH2, CH3, right? So I will get this compound. So with the help of your Wood-Fittig reaction, I will get the desired compound. Okay, but with the help of Woods reaction, we cannot prepare ethyl benzene. Understood? Is it clear? Woods reactions are only used for alkyl halides. Okay, 2 moles of alkyl halides reacting with sodium to give you higher alkenes. And in Woods-Fittig reaction, one should be a alkyl halides, another should be a aryl halides. So this will react in the presence of sodium and diether to give you a aryl arene. Okay, you are going to get a alkyl arene, right? Okay. I hope it is clear. Yes. Is it clear up to here? Any questions? Any doubts? So we have seen some 9 questions. Any doubts up to here? If you have any doubts, please ask. Okay. So let us go for the next one. Which one of the following is an intermediate in the reaction of benzene with methyl chloride in the presence of anhydrous AlCl3? So benzene, so this is our benzene. When it reacts with RCl, that is your alkyl chloride, in the presence of anhydrous AlCl3. Okay, so this is what alkylation. This is what alkylation of benzene. This is alkylation of benzene. So what is the intermediate formed in this reaction? Yes, what is the intermediate form in the reaction? So if I react this CH3Cl plus an AlCl3, what I'm going to get? AlCl4 minus plus CH3 plus. Okay, so our this electrophile is what? Methyl cation, right? So which it is? Option number C. So whenever alkylation of aromatic compounds, okay, when you are doing it with the alkyl halide, okay, in the presence of your aluminum chloride, so this is what? Alkylation reaction. Which alkylation reaction? It is a Friedel-Crafts. Friedel-Crafts, okay, Friedel-Crafts alkylation reaction. Is it clear? It is a Friedel-Crafts alkylation reaction. Yes. Methyl cation is the intermediate. Okay. Option number C. Option number C. Okay. Let us go for the next one. Which one of the following is not formed when a mixture of methyl bromide and bromobenzene is heated with sodium metal in the presence of dry ether? So let us write which of the following is not formed when a mixture of methyl bromide and bromobenzene, okay, is heated in the presence of sodium metal, in the presence of sodium metal, methyl bromide, okay, in the presence of sodium metal in the heated with sodium metal in the presence of dry ether. Okay, so what is the product here? What is the product here? Toluene, right? Toluene is the product. Okay, so toluene is the product here. So which is which of one of the following is not formed? Not formed when a mixture of methyl bromide and bromobenzene is heated. Yes. So what all you are going to get? One product will be your CH3, this toluene. Okay. One will be your CH3 and toluene. Another product, what you can obtain is what? If I have two CH3Br, okay, plus 2 Na in the presence of dry ether, what I'm going to get? I'm going to get ethane, CH3 plus 2 NaBr, right? Then if I have a mixture of uh, this your bromobenzene, okay, bromobenzene plus 2 Na plus bromobenzene again, what I'm going to get? So this and this will attack, giving you a diphenyl, right? I'm going to get what? I'm going to get a biphenyl. So which is not obtained. So we have got toluene, we have got ethane, okay, and this is your diphenyl. So which is not obtained? Propane is not obtained. Option number C. Yes, Tejaswini and Murli have answered it correct. Option number C. Okay. So they have asked when a mixture of, so what we have done? Firstly, we have reacted 2 moles of methyl bromide with sodium and dry ether. Okay, we got ethane. When we took bromobenzene, 2 moles of bromobenzene reacted with sodium metal and triether, we got diphenyl. When we reacted 1 mole of methyl bromide, 1 mole of bromobenzene, we got toluene. So which is not obtained product is propane. So propane, we don't get propane. Okay. Understood? Okay. So please remember these name reactions, very important. Next one, conversion of benzene to acetophenone can be brought by conversion of benzene to acetophenone. Okay, conversion of benzene to acetophenone. So acetophenone is like this. So this is an aceto group. Okay, so this is acetophenone. So how you can get this compound? How you can convert this compound benzene to this aceto group? How we can introduce this acetyl group? Yes. Can we do if we react it with acetyl chloride? Okay, if we do Friedel-Crafts acylation, if we do Friedel-Crafts ElCl3. Okay, if we do what acylation, Friedel-Crafts acylation, then we can get this compound. Is it clear? So benzene, if we react it with CH3COCl in the presence of anhydrous AlCl3, what I'm going to get? I'm going to get the acetyl group COCH3. Okay, so this is a acetophenone. So by using Friedel-Crafts acylation, option number D. Okay, by doing Friedel-Crafts acylation. Alkylation means what? CH3Cl. Okay, yeah, we need to know, we should have the acyl group. We should have the acetyl group or the acyl group. So for introduction of the acetyl or the acyl group, we should use acylation only, not alkylation. Alkylation means we have to get a alkyl chloride. We have to take a methyl chloride. Okay. Understood? So option number D. Is it clear up to here? Okay. Next question. Methane can be converted into ethane by the reaction. So how can we convert methane into ethane? Yes, how can we convert our methane into ethane? First one, chlorination followed by the reaction with alcoholic KOH. B, chlorination followed by the reaction with aqueous KOH. C, chlorination followed by Woods reaction. D, chlorination followed by decarboxylation. Yes. How can we convert methane into? First, we need to do the chlorination. So let us do first chlorination. Okay, chlorination means what? Addition of chlorine. Okay, so how it goes? Just see here. CH4 plus Cl2 in the presence of light. We are going to get, so one of first what? At each step, only one of the hydrogen will be replaced by Cl group. So what I got? I got a methyl chloride. I got methyl chloride. So this is methane. So methane, we did what? We did chlorination in the presence of light. Okay, we got methyl chloride. Now, if I do here, if I take 2 moles of methyl chloride, if I react it with sodium, okay, in the presence of dry ether, can I get ethane? Yes, I can get ethane, right? So plus 2 NaBr. So which is this reaction? This is a Woods reaction. Okay. So chlorination followed by Woods reaction. In Woods reaction, what we require? We require 2 moles of the alkyl halide. So here we can see. Okay. So what we got? We got ethane. Okay. Understood? So we got ethane. So we got a higher alkene. Right. So chlorination followed by Woods reaction, we will obtain uh, ethane. Yes. If we react it with KOH, okay, Murli has answered it as B. So chlorination, okay, if you do react it with KOH, aqueous KOH, we are going to get 2CH3OH. We are going to get a methanol, alcohol. Okay, we are going to substitute the Cl with OH. So we are not going to result into ethane. So option number C is the answer. Okay, option number C. If we react it with aqueous KOH, Cl will be replaced by OH. So we are going to get the alcohol, methanol. Okay, we are not going to get the ethane. Our this is what our desired product is, ethane. Okay, our desired product is ethane. So we have to get the ethane. Okay, fine. Next question. Least energetic conformation of cyclohexene is. It is the, so between the board conformation, least energetic. Okay, least energetic means more stable, right? So most energetic means, so it is the chair conformation. So least energetic means it is the most stable. Okay, most stable conformation of cyclohexene is chair uh, conformation. Okay, so this conformation is the most stable. So remember this, least energetic means more stable, and least least stable means it is more energetic. Okay, so it will be your half chair. Understood? So remember this. Okay, don't forget. So the most stable will be your chair form. Yes, option number A. Very good. Okay, let us go for the next one. The compound that reacts with the fastest with sodium methoxide is. So which compound will react fastest with the sodium methoxide? Yes. Which of the compound will react with sodium methoxide? So the compound which reacts with the sodium methoxide is. The compound that reacts the fastest with the sodium methoxide is. Yes. So what you can see here, nitro groups are there. Nitro group is a electron withdrawing group. Okay. So what is the role of electron withdrawing group? It will withdraw the electron towards okay itself, and what it will do, the electron density will be less, right? So the sodium methoxide. So sodium methoxide in case of your this, okay. So that is your 2,4-dinitrochlorobenzene, right? 2,4-dinitrochlorobenzene. So it will react faster. Okay, because electron withdrawing groups are present. So electron withdrawing groups, what it will do? It will increase the electron reactivity, okay, of your chlorobenzene, aromatic chlorobenzene. So because of that, with sodium methoxide, it will react faster. Okay, option number A. Option number A. Remember that. So what is the reason? Nitrobenzenes, okay, nitro groups, they are the electron withdrawing group. So these electron withdrawing group, what it will do, it as the electron withdrawing groups are there, they will increase the reactivity. Okay, they will increase the reactivity of this chlorobenzene group. So because of that, what will happen? 2,4-dinitrobenzene is the it reacts faster. Okay, fine. Let us go for the next question. The correct statement is, so so there are 4 statements given, so you have to tell which is the correct statement among the following. Okay, cyclohexadiene and cyclohexene cannot be isolated with ease during controlled hydrogenation of benzene. B, 1 mole each of benzene and hydrogen when reacted gives 1/3 mole of cyclohexane and 2/3 mole unreacted hydrogen. C, hydrogenation of benzene to cyclohexane is an endothermic process. D, it is easier to hydrogenate benzene when compared to cyclohexene. Okay, so which is the correct statement among the following? Okay, now when we see the hydrogenation process, okay, when we do so cyclohexadiene and cyclohexene, so these cannot be isolated, okay, when we are doing a controlled hydrogenation. Okay, now when you see a hydrogenation, so only when we are doing hydrogenation, only one compound can be separated. So these two compounds cannot be separated with a controlled hydrogenation. So this is the correct statement. So when you are doing, so when you are having a benzene, suppose benzene is there and we add 3H2. Okay, so what we are doing? We are doing a controlled hydrogenation. We are adding hydrogen. Okay, nickel in the presence of 150 degrees Celsius. So what we are going to get? I'm going to get a cyclohexane. Okay, so cyclohexane and cyclo. So these we have to do a controlled hydrogenation. Okay, they cannot be isolated. Okay, so during controlled hydrogenation of benzene. So option number A is the correct statement. Okay. Identify Q in the following sequence of reaction. Can you identify? So we need to do the reaction. So first is your, so you have a acyl group. Okay. You have a acyl cyclohexane. So you have a compound that you are going to react with PCl5, that is phosphorus pentachloride. So what is going to happen is your, so this is C double bond O. So if I elaborate, so this is C double bond O, CH3. So what is going to happen is your C, Cl, Cl, okay, C, Cl, Cl, and CH3. So I'm going to get this. So your C double bond O is converted into CCl2, CH3. So I'm going to get a gem dihalide. Gem dihalide means what? At the same carbon, you are having two halogen atoms. So gem dihalides. Okay, two halide groups are present at the same carbon. Now further, what they have done, so this is your P, then it is reacted with sodium azide. Okay, sodium azide, excess of sodium azide is taken. So what you are going to get here now, when you have sodium azide, okay, so here your Cl will be, you're going to get triple bond CH. So this is your Q. So I'm going to get alkyne. Okay, option number D. Option number D. So sodium azide, so both the Cl atoms are removed and they will result into a triple bond. Okay, so C triple bond CH. So what it will go as HCl. Okay, 2HCl like that. Okay. Okay, fine. So these were some of the questions for today. Okay, any doubts up to here? Yes, any doubts? Did you are the questions clear? So we have seen some 17 questions today. Okay. So the remaining questions we shall be discussing in the next class. Any doubts? If you have any doubts, you can ask me. Yes. Okay. Okay, fine. So, okay, if you get some more questions, so please solve. So in the next class also, we'll be continuing with the same chapter, hydrocarbons. Okay, so few more questions we will solve on this chapter, and then will be okay. So till then, you also, if you get any more questions, please solve them. Fine. Okay. So I'll end the session here. Okay, we'll meet in the next class. Thank you.